Okay, so welcome everyone. So today we are going to have Enrique Torres from Trinity Western University. So it's great pleasure. So we have the same PhD supervisor, so that's how we have some connection as a same mathematical ancestors. And we are going to hear about sequential motion planning assisted by group actions. So Enrique, please, you can start.
Thank you. Let me make a few comments. So the talk is going to be divided into two parts. In the first part, I'm going to be discussing this idea of sequential motion planning. I'm going to explain what motion planning is in the context of topology. And then the second part is going to be on the group actions aspect of the motion planning problem. So that's what we are going to do. So the first question is, what is motion planning? So the question in general is pretty simple. The idea is that we have a topological space, let's say X, and we would like to provide in a way instructions to some kind of agent, like perhaps a robot, maybe some kind of mechanical system, in such a way, again, that if we provide a couple of points, the planning will consist of a path going from the initial point A to the final point B. So in terms of this context, in terms of this notation, we're going to be considering what we call the evaluation function. This is a function, a map, that is going from the space of paths in X. So I have some notation over here on the left-hand side. And again, it's essentially the space of maps from the unit interval into the topological space X. And what this function is doing is taking a path and then is essentially evaluating the path at the start point and at the end point of the unit interval, and that's going to give us the endpoints of the path. So this path is going to be important in the motion planning problem. And again, the motion planning problem is very simple. Given 2 points in a topological space, what we would like to do is to construct some kind of instruction. In this case, that is represented by a path connecting those 2 points. Okay. So what is a motion planner? So for us, it's going to be essentially a map from some open subspace of the Cartesian product of the topological space with itself. And again, this is essentially just parameterizing a path, as you can see on the left-hand side, that is connecting a couple of points that we provide to the motion planner. So the idea is that we take a couple of points. In this case, the pair is going to be in the open set U, and then S is constructing a path. And this path is going to be compatible with the data that we're providing, the 2 points, A and B. So what we mean by that is that essentially this composition that we have here, the motion planner, composed with the evaluation map, is going to be the identity on U. Okay, so that is essentially what we mean by a motion planner. So it's some kind of like recipe to construct paths given some initial data, A comma B, in the topological space X. Okay, so essentially that is the same as saying that this map is solving the motion planning problem. That is, given 2 points in the open set, we want to find some kind of a stable path in X connecting those 2 points. So something here that is important to notice is that the use of the word stable over here is essentially related to the fact that we want the function, the map S, to be continuous. That is, if there is a small perturbation, let's say over here, of A or perhaps of B. The resulting path provided by the motion planner is essentially going to be a small perturbation of the previous one. So that is the concept of a motion planner, and this is essentially solving the motion planning problem on the subspace U, at least on U. Okay, so that is essentially what we are going to use to define the topological complexity of a space X. This is a concept that was devised, introduced by Michael Farber in the early 2000s, about 20 years ago. So in a way, it's kind of recent. This was introduced more precisely in 2001. And his definition is essentially the smallest number of open sets, U1 through UN, that cover the topological space X cross X, the Cartesian product, for which we have a motion planner S sub I on each of these. So the topological complexity is essentially measuring how many stable instructions, the smallest number, more precisely, of stable instructions that we need to define on the Cartesian product to solve the motion planning problem. So this is a very nice invariant. As I say, this is essentially telling us how many stable instructions we need to solve the motion planning problem in X. Now, a nice property, I'm going to list a few more in just a second, is that there is only one motion planner, that is the topological complexity of a topological space is equal to 1 if and only if the space is contractible. So this is telling us that if we have some obstructions, like for instance, if we are working on, let's say, the Euclidean space minus a number of points, let's say some subset of points, Q, this number, the topological complexity of this space, is going to be greater than 1. So the question at this moment is, how do we compute this number? And well, of course, why do we care about this number? Well, so there's some motivation coming from robotics. And turns out that this number is connected to many, many interesting areas of topology. So I'm going to be discussing a few of them in a few more minutes. So again, if we are studying some kind of interesting space, we're expecting the topological complexity to be a number greater than 1. Okay, so here are some important properties of the topological complexity of a space. First of all, this is a homotopy invariant. So that's a nice property. We're computing a number that is invariant on the homotopy. Second property, the topological complexity can also be defined as the sectional category of the evaluation map. So what is the sectional category of a function or a map? Well, perhaps you know this. Let me just recall very quickly here. So if you have, let's say, some kind of like function map from, let's say, a topological space E to B, another topological space. The sectional category is the smallest number of open subsets covering the base. In this case, the notation is B, on each of which we have a section of this map, let's say P. So that is the sectional category, the smallest number of open subsets that cover B, on each of which we have a section of the map P. So that is essentially the sectional category, CCAT, of P, the smallest number of open subsets. This is also known, perhaps some of you are familiar with this, as the genus of P, or the Schwartz genus of the map P. So there are many connections of this with other areas of topology. Like for instance, in the if I recall correctly, 1970s, some people were making connections, like Stephen Smale, for instance, was making connections between the concept of sectional category and other problems in algebra. Okay, so another, let's say in a way, kind of technical properties is that this number, the topological complexity, is bounded by the category of the Cartesian product. So what is the category of a space? Well, if you have a topological space, let's say X, the category, or let me use different notation, perhaps I can use, again, maybe capital B. So if you have a topological space, the category is essentially the smallest number of open subsets that cover your topological space that are contractible in B. So that is a category. Or some people know this as the Lusternik-Schillerman category of the space, LS-cat. So this is another concept that is that has been around for a while in topology, and in this case it has connections to analysis, to differential geometry more precisely. So the TC is bounded above by the category of the Cartesian product, and we can compute lower bounds using, for instance, cohomology. So here we have one that is very, very useful and is defined as the zero cup length of the space X. So what is that? Well, the zero cup length is essentially the cup length of the kernel of the diagonal map. So here delta, as you can see on the right hand side, is the diagonal. So when you look at the kernel of the diagonal, well, those elements in the kernel are called the zero divisors. In this case, give me just a second. I just realized I have this is in cohomology. The map goes in the opposite direction, like this. Okay. So if you have essentially an element in the cohomology of the Cartesian product, let's say something like U times V, the diagonal going in the opposite direction is essentially affording the cup product. So the cup length of the kernel is essentially what we call the zero divisors cup length of the space X, and this is very useful. And well, in a way, these are the main tools, number 3 and number 4, that we use for calculations of the topological complexity of a space. There are some limitations, of course. There are cases when people have to use other devices, like for instance, obstruction theory, to be able to compute the exact value of the topological complexity. So these are basic, but they are very useful. And there are, let's say, some refinements of these bounds to compute the topological complexity of a space. Here is another one that is very useful and is essentially in terms of the dimension of X. So here I'm going to assume that X is some kind of nice space, like for instance a CW complex. And is in terms of the dimension, as you can see, and it's also in terms of the connectivity. So as you can see, if Q is the connectivity of the space X, this is telling us, this inequality, that if the space is highly connected, the topological complexity of the space is going to be very low. So this is another important piece of information, another tool that is used a lot in calculations of the topological complexity. So I'm going to show you just a few basic examples, and then I'm going to transition to the next part of the talk on how we use group actions in the context of the motion planning problem. So here is the first, perhaps most basic example of topological complexity. It can be shown using some arguments of, in this case, the connectivity, or more precisely, if you want, the dimension of the m-dimensional sphere and also using zero divisors, it can be shown that the topological complexity is either 2 or 3 depending on the parity of the space. And this is to be contrasted, to be compared with, for instance, the category of a sphere, which is always 2. So the topological complexity at least is telling you that it is detecting what is the parity of the dimension of the sphere that we are using. So that's a nice property, and well, more can be said. For instance, in this case, I have this example. I'm not gonna, of course, try to prove it. It takes quite a bit of time. This is due to Farber as well, Tabachnikov, and Jusvinsky. So they prove that the topological complexity of the projective space is essentially the immersion dimension of the projective space. So the immersion dimension is essentially the dimension of the smallest dimension of a Euclidean space in which the projective space admits an immersion. So this is a beautiful, beautiful result because it's making a connection between this simple looking homotopy invariant, which is the topological complexity, with a very, very difficult problem in topology. This problem was studied by many, many people in the 1960s, and still some people are active studying the immersion dimension of some spaces, like the projective space, but turns out that it's very, very difficult to compute. There are many calculations available, but again, it's an incomplete problem, an open problem. And again, I think the emphasis here is that the TC on one hand can be very, very easy to compute in some cases, like for instance, in the case of the sphere, it's very easy to come up with some explicit motion planners, explicit instructions to complete the calculation of the TC of the sphere. But on the other hand, there are situations like in the case of the projective space when computing this is essentially hopeless. It's almost impossible at this moment to compute this. Now, we would like to extend this, if you remember the title of the talk, sequential motion planning, to more points. So the case of TC is the case on the left-hand side when we have essentially just 2 points and we want to construct paths connecting that initial data. And sequential essentially refers to the case when we have more points. On the right-hand side, essentially I have again a couple of points, A1 and AN, and now I have some intermediate, let's say, stops or points that we would like to visit with some maps, with some paths that we are going to construct. Okay, so now instead of using only one evaluation map, we're going to use what we are going to call the multi-evaluation. So we're going to take the unit interval and divide it into subintervals of the same length. And we're going to consider, again, the multi-evaluation function. And it's taking a path and it's evaluating the path at the endpoints, 0 and 1, and also these intermediate subdivision points that we have here. So the connection again between this multi-evaluation map and the motion planning problem is that instead of visiting only 2 points, we want to visit a number of points in some kind of order, like A1, and then A2, A3, and so on and so forth. So this is an extension of the classical motion planning problem, and this is affording what we now known as the nth sequential topological complexity. It's essentially the sequential, the sectional category, excuse me, of the multi-evaluation map. So we have our function E sub n going from x into the Cartesian product, and essentially what we want is the secant of the multi-evaluation function. So this is a concept that was introduced by Julie Rudiak in the late 2000s, roughly. And well, this one is one of the many versions now available of TC. TC so far, the one that I have introduced, is essentially a family of homotopy invariants. TC2 is a classical one when we have only 2 points, and then we have, of course, TC3, TC4, and so on and so forth. There are very few calculations, explicit calculations, for higher values of TC. At this moment, most people have been focusing on calculations of TC2, the classical one. There are some calculations for higher versions of TC, and again, there are more versions of TC today available for other purposes.
So
So here,
are they
yes,
comparable? The two.
yes, they happen to be comparable. For instance, in this way, they provide a sequence of homotopy invariant, a non-decreasing sequence of homotopy invariants. And well, there's more information. For instance, Rudiak proved that they grow at most linearly in terms of n. And n is in this case essentially the index that we are using for the definition of TC. Yes, so there are some calculations. Here I'm just going over a few just to give you an idea of what is the kind of things that people have done, have computed. Here is the calculation of the higher TC, the nth sequential TC of the sphere. So in this case, again, is related to the parity of the sphere. So it's dictated by the parity, and also is dictated by the order of the TC that we're using. So that's nice. The calculation in a way goes in a way similarly to the calculation of TC2. We have to compute some zero divisors to get a lower bound. And in the case of the odd dimensional spheres, we can produce explicit motion planners to improve, and in this case, more precisely, lower the value of the TC to only n. So that's, again, kind of the typical calculations. Let me show you one more over here. If you consider the configuration space, essentially, the notation I'm going to use is Fnx, consisting of tuples in the Cartesian product and tuples in the Cartesian product with no two entries the same. The higher TC, the sequential TC of this space has been computed. Notice it's also in terms of the parity, as you can see on the right-hand side, of the Euclidean space that we consider. So I'm going to look at this particular case. And it's in terms also of the order of the TC that we're using, and also the number of obstructions. This is a nice calculation. Requires some technology in terms of obstructions and also zero divisors cup length calculations. And what is nice is that this is essentially related to the motion planning problem in, let's say, a Euclidean space. I'm going to just look at, for instance, the case of R2 with some obstructions. So essentially, we want to construct paths or multipaths um, that do not collide in RM, or in this case in R2. So here we have this calculation. This was computed by by Grant and Gonzalez. And well, this is another nice example of TC that has been completed. Okay, so this has been just like a brief introduction to the concept of TC and higher TC, so that you have an idea of what is the talk about. So now I'm going to move on to how we can incorporate group actions to the context of topological complexity. Okay, so that is the second part. Okay, so suppose that we have a finite group and that this group is acting on a topological space. So here's a nice example. I like presenting this. And well, here what I'm thinking of is that we have a crane that is revolving, that is rotating. So this little kind of shape I have here is a crane. And here we have, let's say, a copy of the Euclidean plane. And I'm thinking of the Euclidean plane minus a point, because here in the case of the crane I have in this picture, I'm assuming that the crane is based, is essentially sitting on a point, and that's a point that we are going to be removing because the crane is occupying that point, and the crane is essentially rotating and is picking up some objects, rotating, and then delivering those objects somewhere. Think of this perhaps as some kind of like construction site. And well, here we have a topological group, in this case, the Lie group O2, acting on this space. And again, you can think of this as some kind of like crane revolving around, taking some objects and then delivering them somewhere else. You can also discretize this example to some kind of like, for instance, cyclic group. There are cases, for instance, when some cranes can perform only rotations through certain angles. So you can think of that as some kind of discrete version of the Lie group action that I'm representing here with this construction site example. So the question is, well, if you think about, let's say, the motion planning problem here, let's say you want to go from some point over here A to some point over here B, what you could say, well, is why don't we take advantage of the fact that the construction site has a crane working here, and then we can say, well, lift this up, rotate, deliver it over here, and then construct a path over here from, let's say, A prime to B. So that's the kind of thing that we would like to do in the context of the motion planning, incorporate the group action into the study of this question, this problem. Okay, so something that I think perhaps should have mentioned from the beginning of the talk is that we are not going to be using in our calculations and examples pathological spaces. We're going to assume that we are always working with nice spaces. That means essentially Hausdorff path connected, locally path connected, and compact spaces. Again, there are some corner cases, some situations that we could say are pathological, where some of these calculations and some of these constructions could break down. So we are going to assume that that's not the case. For us, we will be using only nice spaces. Now, when I said we would like to incorporate group actions into the study of topological complexity, there are two possibilities. There are two notions that have been already introduced. One of them is when we want to make the planners, remember the sections of the evaluation map, compatible with a group action present in the topological space. So that is one of the notions associated with this idea of incorporating group actions to topological complexity. There are already some constructions. One of them is known as the equivariant TC, introduced by Coleman and Grant. Again, essentially what they want is to make the planners compatible with the action present in the topological space. And there are some other variants of that construction. For instance, here I have the strongly equivariant TC, introduced by Nishnikov, and the invariant TC introduced by Lubasky and Marcentowicz in Poland. So that's not what I'm going to be discussing today, but I would like to mention that because it's kind of part of the history of this question about the incorporation of group actions to the study of the motion planning problem. What I would like instead is to focus on making the group elements be part of the motion planners. And that's different. And well, that is in a way connected to the example of the crane that I was mentioning just a few seconds ago. So there are two notions already available. One of them is the effective TC of Kaluba and Blasik and Kaluba. And the other one is the effectual TC of a number of authors, Cadavid, Gonzalez, Gutierrez, and Ipanake. They introduced this one, which is kind of an extension in a way of the effective TC, and is also providing a connection to the classical TC, in this case of a quotient space. So I'm going to explain more about that in just a few minutes. So these are the two possibilities, and I will be focusing on the one on the right-hand side, making the group elements part of the motion planning. So here is the construction of the effective TC of Blasik and Kaluba. So instead of using the space of paths, remember in the case of the construction of TC, we go from the space of paths using this notation. If you want, using the evaluation function, the evaluation map into the Cartesian product. So what they did is that they replace this space by the space of what we could call broken paths. So what are these? Well, essentially, these are paths consisting of two components in such a way that the endpoint of the first component is part of the orbit of the start point of the second component, as you can see in this graph I have over here on the left-hand side. So here's a technical description, and well, based on this idea, we also have an evaluation function. So if you take the two components, what I can do is take the start point of the first component and the last point of the second component. Okay, so notice this is extending the classical construction. For instance, if the group is trivial, you are essentially just recovering the classical construction. So here I have this definition. The notation is kind of cumbersome. TC G2, the 2 is because we have essentially two components. The G is because we are making use of the group action. This is by definition, this version of Blasik and Kaluba of TC is the SICAT, the sectional category of this evaluation function. Okay, so in a way, notice we are making use of the group action. So somehow, some way, we're leading to the person planning, the motion planning, to use the group elements to complete the motion. Okay, that was refined by Cadavid, Gonzalez, Gutierrez, and Ipanake just recently, only like a year and a half ago, roughly, perhaps less. They introduced this, the effective TC that they constructed. Instead of using only components, in this case paths, they also want to keep track of the group element that can be used to glue these broken paths. So I'm just going to scroll up to show you the difference again. So notice in this case, in the construction of Blasik and Kalubi, we are essentially just taking two components that can be glued, that can be patched. Now in the construction of these people, we are taking the two components and we are also keeping track of the group element that we can use to glue the broken path. So similarly, we have an evaluation function, and this affords the so-called effective TC that we're going to use. The effective TC, now notice the index 2, because we have essentially two components, is the SICAT, the sectional category of this evaluation function. So that's nice, because now we are just saying, okay, don't look only at the components, please also keep track of the group element that we want to use to complete the motion. And again, think about, for instance, the example of the crane rotating, revolving around some point. That is kind of important in many applications, because you could say, okay, here is the crane or the mechanical system assisting the planning, but we also want the instructions of the mechanical system to be part of the planning so that we complete the motion. So that is the effective TC construction here. And well, let me mention a few properties. Both of these constructions, the effective of Cadavid, Gonzalez, Gutierrez, and Ipanaki, and the other one of Blasik and Kelubi, both of them are G homotopy invariants. And they are related in this way, as you can see in this inequality. Both provide lower bounds for the regular TC of the topological space X. So in a way, they are nice approximations of TC, the classical one, and the one I will be paying more attention to is this one, the TC of Gonzalez, this one. So we are approximating TC from below, and well, we would like to see how far in applications, how far this is from the regular TC. In a way, we would be thinking, well, if we are making use of the group action, we should expect perhaps the one on the left-hand side to be perhaps in some cases way lower, because the group action could be facilitating the motion planning in many ways. Okay, so here's another refinement of this idea of making the group elements be part of the motion planning. This construction is called the effectual TC. This was also introduced by Cadavid, Gonzalez, Gutierrez, and Ipanaki. Perhaps from now on, I'm just going to refer to the construction of Gonzalez for short. I know there are 4 people here. Just for simplicity, let me just refer to Gonzalez here. And well, what they did is that they constructed this function. They consider this function on the right-hand side. They have the space of paths, then they take the usual evaluation, and then they compose the evaluation with the identity Cartesian product, the projection function. Okay, so essentially we are taking a path, and then we are taking the initial point, okay? And then the second component for this composition is the orbit of the endpoint of the path alpha that we take at the beginning. Now here, for simplicity and also for some technical reasons, I'm going to assume that my group action is free. Let me just say quickly here that the main reason is because I want this component here, the function pi, to be a vibration. So I'm going to assume for simplicity that we are using only free actions. Okay, so why is this important in the motion planning context? So as you can see here in this note, I'm essentially noticing that a planner is connecting an initial point A with a point in the orbit of the other point in this notation B. So what's happening here is that we are saying, okay, here is A and over here is B, but instead of going to B, starting from A, how about if we content ourselves with going to some point in the orbit of G? And that's what this is essentially saying. Okay, so be happy if you can make it to a point in the G orbit of B, because if you land in a point in the orbit of B, that's it. You can just say use the mechanical system, the group action, to go to B. So that's essentially the interpretation in terms of the motion planning problem. Okay, so here are some properties. This effectual, that's the name, the effectual TC is also a G homotopy invariant of X. So that's another nice number that we would like to compute. And moreover, it's related to the effective TC and the TC of the quotient space. Notice over here, the quotient. So that's nice, because in the past, people were trying to say something about the TC of a quotient space. For instance, if you remember a few minutes ago, I was saying that there are 2, let's say, ways we can study a group action uh, helping us in the context of the motion planning problem. I said, well, one of the ways is by looking at motion planners compatible with the group action. And well, in that way, people were trying to say something about the TC of the quotient space, but the kind of results that they were getting in most cases were very, very weak or not useful enough to provide enough information about the TC of the quotient. Whereas in this case here, we have a nice connection, and we're expecting that the effectual and the effective TC would be nice approximations, strong enough in some cases for the TC of a quotient space. So for instance, think of, for instance, something like maybe TC of the projective space, which is a quotient, of course, is essentially just a quotient of the antipodal action of the cyclic group of order 2 on the n-dimensional sphere. So that would be perhaps a nice calculation. Here I'm kind of like trying to sell you the product, but is just an example, of course, in this case. Okay. Now, what I have done recently is that I have extended these constructions to the higher context of TC. What is the higher context? Well, essentially that refers to sequential TC. Now, I'm gonna again focus only on two, the effective and the effectual, and I'm also going to introduce another one that I called the orbital TC. And again, there are many, many versions of TC available today. As I mentioned, for instance, the equivariant versions, the sequential versions, and now I have this one, and there's other ones, like for instance the symmetrized versions, the symmetric versions of TC. There are many. I could say perhaps there are dozens of versions of TC available, each of them serving different purposes. So here I have this definition of this space M sub n G. The M stands for multi-paths, and well, the G is because, well, we want to make use of the group elements. So here in this case, I'm extending the construction of the effective TC of Gonzalez. I have a broken multipath, and I'm also keeping track of the group elements that we can use to glue this path. Now, in this case, what I have is a broken multipath that is emanating, starting from the same orbit, as you can see in this graph over here. So I have a bunch of components of paths, and we could glue this. By the way, I think it would be a nice moment here to make another comment. Just a few minutes ago, I was saying that the TC sub n of x, the nth sequential TC, is the sectional category of the evaluation, multi-evaluation, which goes from the space of paths to the Cartesian product. This space of paths can be replaced, and it's going to be affording the same number, by the space of paths from the join. So in this case, G sub n is the join of n copies of the unit interval. So that is something that can be visualized in this context as some kind of like a spider thingy here. So we have like a point. So this is happening in X. And then here we have a bunch of paths, alpha 1, alpha 2, emanating from the same point. So both versions, the sequential and this kind of like a spider version, are equivalent. Okay. So that is why I defined this space of multipaths here, essentially consisting of a bunch of components that can be glued, and we are keeping track of the group elements that we can use to complete the motion planning. So we have an evaluation function again, and then we're taking the sectional category. Okay, now it turns out that the group elements can be waived, can be forgotten. You don't have to carry them if the action is principal. So that's a nice property here, because in some cases when you are constructing explicit motion planners, you perhaps in some cases you don't want to carry that information with you, but of course if you need it for some specific purposes, you can also include it as part of the information, the data. Okay, so let me go slightly faster here just to uh, give you a little bit more of the things that we have done recently on these aspects. So how about the effectual one? Well, the effectual one is similar to the construction that we had before. Instead of using only one quotient space x modulo g, we're using n minus one of them. So the idea is in a way similar to what we had before. We have a point, let's say A, let's say the source, and a bunch of targets. Maybe perhaps we can do something like this. B1 is the target, but we are going to content ourselves if we can construct some kind of multipath like this that is emanating from some point and is reaching one of the targets, in this case A, and the other ones we are going to content if they can be just elements in the orbit of the targets. Okay, so these points over here are essentially illustrating, representing the orbit, and we are going to be happy if we reach at least a point in the orbit. So again, think about the example of the crane, and well, that's the kind of things that we can do here with this. And well, you could say, well, why not all the elements? Well, that gives rise to the higher orbital TC. So instead of reaching perhaps all the elements that we want, about if we content ourselves if we reach elements in the orbit of each of them. So this affords what we called, or I called, this is a definition that I proposed, the higher orbital TC. So these are extensions um, mimicking the construction of Rudiak of the sequential TC, now in the context of effective, effectual, and orbital TC. Okay, so some properties. These constructions, the higher, effective, effectual, and orbital TC, all of them are G homotopy invariants, and they are related in this way, as you can see through these inequalities. The effective is the first one, and then we have the effectual. Notice now the notation, we are indicating some kind of order associated to the number of points in the motion planning problem. And we have, again, the effective, the effectual, the regular TC of the quotient space, that's nice. And now an upper bound, which is the orbital TC that I defined just a second ago. Now, another nice property is that given that these constructions are in terms of sectional category, we can also speak of lower bounds in terms of zero divisors. So that's kind of technical, it's not difficult to establish, but we also have zero divisors in the context of effective, effectual, and orbital TC. So that is useful for many calculations. Now, I also have to tell you that yes, people compute these numbers. They are very happy. They are able to compute, for instance, the TC of the Klein bottle. For instance, that was a very, very difficult calculation. It was completed just a few years ago. It took more than a decade to be completed. Imagine just the TC of the Klein bottle took more than 10 years to be calculated. And okay, we have the numbers, nice, fantastic, but what is the point of that? If we are honest, um, perhaps we could say that the calculations in a way are not very, very relevant. What is more relevant is seeing the connections of these calculations to other areas, like for instance, the immersion problem I mentioned of the projective space, and thinking of future possible applications. What would be nicer is to complete these calculations by means of explicit motion planners. And that has been achieved in some cases, not in all cases, but in many cases, there are explicit motion planners realizing the values of TC. And that's nice because that could be used in future applications. Again, those are essentially the main tools, the zero divisor scope length, connectivity, inequalities stuff in terms of the dimension, and also explicit motion planners. And in my case, I regard the last one, the construction of explicit motion planners, as perhaps the most important one, because it could be nice for and useful for applications. Here's another result. I'm not going to go over the proof. I was thinking of going over the proof of this. I'm just going to mention the result. The effectual TC can be bounded below by the category of the quotient space in this way. More precisely, the quotient is the Cartesian product of the quotient space, as you can see in the screen. So I have the proof here. I'm going to skip it. I know I'm running out of time in a few more minutes, so I'm just going to again tell you I'm going to use this in an example in just a few minutes. Okay, or more precisely in a few seconds. Another property here that is important to mention, if you recall the definition that I gave you of TC, we say, well, or more precisely, the sectional category of a vibration or a map is in terms of open subspaces covering your space, your base space. That property can be waived, can be replaced by something, let's say, more convenient for applications if the space, the base space is nice enough. Let's say we have spaces like ENRs, for instance, CW complexes will do. If we have nice spaces, the openness condition of the planners can be replaced by uh, the condition that the domains are just ENRs defining a partition of the space. That is essentially spaces, subspaces that do not overlap. And that is very useful in the construction of explicit motion planners. People like, for instance, Farber used this in his early calculations in the 2000s. He noticed that he could replace the openness condition by this, let's say, in a way more convenient requirement for explicit calculations. And well, it turns out that the observation of Farber can be carried out to many other contexts, like, for instance, in this case, to the case of effective, effectual, and orbital TC, and many others. Okay, so I'm just going to present you a few more calculations, and then I will be wrapping up in a few more minutes. Here's an example of the antipodal action, and more precisely, the calculation of the effective TC. I'm just going to quickly tell you what is the kind of things that you can do to construct explicit motion planners. And again, that would be, let's say, nicer than just simply computing these using, I don't know, for instance, connectivity bounds. Here I have these domains, use of J consisting of tuples of the Cartesian product of a sphere with the condition that exactly J components, so what is J? J is essentially the index, with exactly J components different from the first component of the tuple. Okay, so automatically you see that these are defining a partition. Okay, so that's again related to the comment I just made a few seconds ago that we can replace the openness condition in nice cases, like for instance, the case of a sphere is a CW complex, and therefore it is also an ENR, Euclidean neighborhood retract. And well, here I'm defining this path alpha by cases. If y is equal to x, if the target is equal to the source, essentially we're going to take the constant path. Now, if y is different from x, think of the sphere. So for instance, here, let's say it's y, and over here is x. Then over here, we are going to have negative x, and these two are not going to be antipodal, so we can speak of the shortest path over the sphere connecting these two guys. So that is the notation I have here. So the square brackets I have here stand for the shortest path connecting, in this case, minus x with y. And again, that can be done because y is not equal to x. Therefore, y is different, or is not antipodal with negative x. Okay, so my planner that I defined is this. Given a tuple, x1 through xn, define a bunch of paths using x1. So I will be constructing essentially a broken multipath emanating from x1 or negative x1. And then that's what we're going to use to reach the other points. Now, you could say, well, that's nice. What is the issue? The issue is that this could not, in some cases, be stable, and the stability can be provided, can be checked if we restrict this motion planner S to the subsets that I defined over here. That's where we have stability. And that is therefore telling us that we can show this inequality. So we have sections, we have at least n of them. Therefore, the effective TC is going to be less than or equal to n. Okay. Now, the lower bound can be computed using zero divisors. So I'm not going to mention too much about this. It's something that is technical, but it's not difficult. Therefore, the effective TC of a sphere is essentially just in terms of the order of the TC that we are using. So that's the calculation of the TC. The effectual TC can also be computed in some cases, not in all. The main tools are inequalities. For instance, if you have vibration, let's say going from E to B, it's known, that's something that can be checked easily, that the sectional category of this vibration is less than or equal to the category of the base. So using that, we have this upper bound, and this lower bound is the one that I mentioned just a few seconds ago as well. So with that information, we have this result here. So notice, these are telling us that we almost have the calculation of the effectual TC of the m-dimensional sphere. Now, it turns out that it's possible to settle the calculation when m is equal to 1, 3, and 7, which could be suggesting, so those are the cases when the sphere is parallelizable, which again, this could be suggesting that potentially, and this is just a conjecture, kind of like a wild conjecture, potentially the effectual TC might be connected to the Hopf-1 invariant problem. But again, this is an open question. We don't know what is the final answer of this calculation. This is so far what we have, and again, it could be connected to some potentially nice results from topology. The orbital TC of a sphere can also be computed. I'm not going to mention too many things about this. The diagram I have on the left-hand side can be used to provide a lower bound with zero divisors. And the upper bound is coming essentially from dimensional reasons. And well, the calculation of the orbital TC can be completed, and is this value you have on the right-hand side. So that's nice. So going back to the properties I showed you, perhaps you remember this a few seconds ago, this inequality, that we have the effective first, then the effectual, then the quotient space, and then the orbital. Here's a very explicit example for the four-dimensional sphere. The effective is equal to 2. Okay, so that's a calculation. And then the effectual, we don't know, but it could be something like 5 plus perhaps 1 or maybe 0. And then we have the regular TC of the projective space. That one is known, is one of those cases that is known, is equal to 8. So notice we have 2, 5, 8, and then the orbital can be computed is equal to 9. So that's telling us that these values can, of course, be all of them different, like in this case. And well, as I mentioned, some of them are still unknown, like this. We don't know what is the magnitude, for instance, of this. Okay, so we're computing, the point of this example is that we're computing invariants that are different. They are not repeating in general. And I'm gonna close with this result that is coming from a paper that I posted on the archive just a few months ago. And it's essentially summarizing the kind of calculations that can be completed using this technology. So here in this result, and again, this is what I'm gonna use to close my talk. I have a Riemann surface. It's a compact, closed, orientable surface of genus at least one. And then I also have the m-dimensional sphere, and I have the results of the effective, effectual, and orbital TC. For all of these cases, I have, for instance, the rotation action on Riemann surfaces with genus, a number that has to be odd. Okay, so if you have, let's say, something like this is a genus 3, and let's say this is in the Euclidean three-dimensional space. Let me use this color instead. Essentially, the rotation action I have here is the rotation, let's say, about the z-axis, the z-axis in this case. Okay, rotation by 180 degrees. Okay, we have the reflection, and we also have the antipodal action on these spaces. And here all the calculations using dimensional bounds, zero divisor scope length calculations, and in some cases explicit motion planners. So some of the values are still again open, unknown. Like you can see here, we have some indeterminacies, like I call them here delta, that could be 0 or 1 in some cases, but many of the calculations are also complete, like for instance, the case of the orbital TC in the case of the antipodal action. So I'm going to stop here because I know I'm over time, and thank you for your attention.
Okay, thank you, Enrique. So very nice. Okay, so any questions for Enrique?
Just going back to the m equals 137 in the TC calculation that you had. Where did you get the 137? Like, what was the, like it says you can settle the calculation. So
yes.
What helps you with the 137 to settle the calculation?
Yes. The calculation can be settled in these cases because those are the dimensions of the parallelizable spheres, and those are the cases where we have a nice algebraic structure over the corresponding Euclidean spaces. In this case would be the complex, the quaternions, and also the octonions. So using those algebraic structures is possible to construct explicit motion planners that improve the upper bounds obtained by dimensional and connectivity reasons. So that is essentially the answer, the main reason why we have these calculations.
There is another place that this 137 shows up, and you have a action of a product of spheres with C2. These are the dimensions that you can say the action is trivial on the homology. That's why I'm asking if there was any connection to the action on the homology of a product of spheres shows up.
No, I couldn't hear the question very well, but you're asking whether there is some connection to the cohomology of quotient spaces. Is that what you were asking? Sorry, can you repeat your question? I couldn't hear very well.
These are the dimensions on the problem of studying free actions on product of spheres.
Oh, okay.
That these are the dimensions that the action on the homology may be non-trivial, and these are the open dimensions for that reason.
Oh,
I
okay.
wonder if connection to product of sphere actions.
Good question. I could say I do not know if there is any connection between this calculation and the problem, the fact that you are mentioning. There might be perhaps a connection somehow, some way. But again, the calculation is coming from the fact that these are the parallelizable cases of the spheres, and there is some algebraic structure on the corresponding Euclidean spaces that can be used for constructions of explicit motion planners. There might be a relation, but I do not know at this moment.
Thanks.
No problem.
Thank you. Yeah.
You're welcome.
Any other questions? I have a small question. So in the case of the lower bounds that come from zero divisors, so in the equivariant context, do you use some sort of equivariant homology or?
Let me recall. I think in those cases, yes, there are some calculations using, I think Bredon cohomology for these zero divisors coupling lower bounds. Yes. Now, in a way, I could say people have abandoned those calculations. There are not many new results recently because the calculations are difficult, technical. And I think it's also kind of related to this comment that I have been mentioning, that yes, you can compute, but the point, the inspiration after all of these invariants is the motion planning problem. And I think the difficulty of the calculations in a way reflects that we should be, instead of focusing too much on calculations, we should perhaps think more of connections between the motion planning problem and other intrinsic properties of the spaces.
Yeah, and the other thing, so when you first start talking about the equivariant case, you divided it into two groups of invariants. So and then you focused on the ones on the right. So is there so the reason you divided them into these two groups is because they group among themselves, or is that just an artificial division between the two classes here?
Well, the definitions are in a way kind of like different. Again, the one on the left hand side is more on the compatibility, that the group action respects the motion planning, whereas the one on the right hand side, we are saying now we want the group action to be part of the motion planning. Now, what I was saying just a second ago is that the compatibility condition happens to be perhaps not very natural in some applications, and besides that is technical and difficult to compute in many cases.
I mean, so looking at equivariant sections would be a natural definition, and that's the one on the left, right? Instead of looking at these jumps. Okay.
Yeah.
Okay.
It is natural indeed. At the same time, it's difficult to compute.
Okay. Okay. Thanks. Any other questions for Enrique? Okay. Otherwise, let's thank Enrique. Thank you very much. Thank you.